Now, today, we are going to have a continuation of chapter 36. But before that, I would like to have a. I asked you guys last night to finish the MCs. Have you all done that? Have you all done that? MCs. Have you all done the? Have you done all the MCs? Yes, that's right. Okay, good. So shall we check your understanding of those? Okay, so I would like to refer to the book again. Sorry, I need to open them. Yes, where are we? Oh, oh yeah, here. Oh, I just find it very, very strange. I don't know why I cannot press anything else. Just wait for me. Oh yeah, this is the one. This is the page. Yeah. So we would like you guys to take a look on this one. Chapter 36. Now we just stop it here, right? So yesterday we just come up with some of the calculations on finding the rate of reaction above from the graph. How? Now, it really depends on the rate of reaction we are going to have, right? So we have got average rate and instantaneous rate. Average rate is very, very simple, okay? You need not consider the curve. You just mention a change in amount of substances over time and do the average data, right? Just like delta y over delta x, and you may get the answer. But once you are asked to come up with instantaneous rate, it is rather difficult. Do you know why? Someone tell me, why is it so difficult? What you need to do? Now we have got two rates, right? One is average rate, right?
Yes.
What is instantaneous rate? Now today, I would like to ask you, right? Instantaneous rate. How can we get the instantaneous rate of the reaction? How? First of all, you
slope
yes, slope. Yes, slope. Slope of what? It is a curve, right? It's a curve. So when you have slope, if you consider the slope, they will have different slopes at different time. So how would you use one scientific term, right? Something like mathematics. How would you say that? Start with T. Anyone who can help? Start with T. Yes, tangent, right? You are going to find out the slope of the tangent at certain time. At certain time. So this is what it is rather complicated. So that's why yesterday I asked you guys to draw a this is the tangent, right? The one is straight line, the black one is a tangent. This is tangent and another tangent. So it will tell you a specific time, a very, very short moment. What is the rate of change of substances over time? So what is mean by that? Yesterday, I just give you a trick, something like this. It's like imagine that you are going to magnify the graph, magnify the graph, magnify the graph, magnify the graph, and you are choose certain points for consideration. For example, you are going to consider this point. Tell me what is the instantaneous rate at this one. So what you are going to do is to draw a triangle like this, and you just magnify it. Okay, you just magnify it. Okay, you just magnify it, and such that you can get this black line. Okay, this black straight line. I use this to calculate the slope, and this is what we call it an tangent at a certain time. Do you understand? Now this is what we shared with you last night. Now today, I would like you guys to have a recap on those MCs. Those MCs. Take a look. How many of you have done that? Could you please put up a hand? How many of you have done that? Please put a tick. Those MCs. Just 2, 3. Huh. Do you know what are those 4 questions? Anyone who can type it onto a chat room, let others know. What are those 4 MCs? Well, just 3. Come on. You just have 3. 3 of you who just finished it. 4. 温子慧. Let's take a look. Hey, 龐家豪, you're here, right? Good morning. 李彤. And who else? Who? All gone? Oh, 陳偉豪, the 4 one. How about the others? 6, 7, 9, 10. Doesn't matter. Doesn't matter. And try to see how will you deal with it, right? 6, 7, 9, and 10. Take a look on question 6. Now it is on your book, page 25. All of you, please turn to page 25. Now consider the reaction shown below. So you have got this, right? 2 to 1. Yes, that's right. So you are going to tell the X was contained in a gas syringe during the reaction. Origin is X, right? So which of the following graphs shows the variation of number of rows of X and X2 with the time during the reaction? So with no number here, you are going to consider what? Consider the row of this. So we have going to have 2 chemicals. One is X. What is X? It is a reactant. So we have got 2 moles of reactant to be consumed. So what will happen? They will have 1 mole. 1 mole of X2, 1 mole of product to be formed. Okay? So that's why if you are going to show this one, X, it should be what? It should be reactant. So what will happen finally for X? They will drop in amount for X. You understand? They will drop in amount. So you are going to check X, they will drop. So D is not correct. Okay, D is not correct. Can you see that? X increase. So you're going to find out this one drop, this one okay, this one's nice, it drops, and also this one drop, also okay. Can you get my point? So you may get A, B, and C. Why is it B? Could you please tell? The mole ratio. RH. What's that?黎雲正, why you think it's B?
阿 Sir， 講唔講得嘢啊？而家
Question 6. Can you see that?
因為佢等一陣，唔係應該係 C， 我睇錯咗。
So
因為你 X 比 X2 係2比1咯，即係佢係2個，跟住係咯2個比1咁樣，跟住之後所以就係係咯所以就係 C 咯，2比1。
You think it is C? You think it's C? How many of you think that it is C? Could you please put up a hand? Tell me. You think that it's C? 1. Just 1. Just 1. Put up your hand. C. How will you understand this C? Now you will see that it shows you y-axis. It tells you to change an amount of X and X2 over time. Okay, so you will be put it as a general way with number of moles. Okay, so it will drop at a certain height. That certain height, if you treat it as 2 units, okay, 2 units, 1 unit and 1 unit, and you can get what I mean, right? So just focus on this curve. Just focus on this curve. What is the drop? X will drop as 2 units. Can you get my point? So what will happen is on the product. The product, they will increase in what? They will increase in 1 unit. So which is C, it is correct because C, which shows you it is in line with what is written in the equation. Can you get my point? So remember, if you consider that type of reactions, you are going to find out the equation first and check what. There's a very important data that you need to check. Check what? The mole ratio, right? The mole ratio of the equation. Can you get the point? Okay, this is number 6. Questions? Anyone who have a problem, who have any problem, could you please let me know now? Find it difficult? No? Great. So take a look on the other question. It is 7, this one. Now, similarly, you use the same tricks, right? You have to tell. Lei Tong, could you please explain your answer? C, many of quite a number of you C. C, yep, C. So how to explain? Explanation, please. Dead silence. Who would like to have a try on the explanation? You may turn on the mic and tell. First of all, Luan Ziwei just say that rate of consumption of X equal to rate of formation of Y. How will you know? From the data, right? So you may see this one, it is 0.100 and it will drop to what? Yes, you may use this line. Some of you love to use this one, no problem. It is a very good reference point. Now, if you choose this one, if you choose this one as a reference line, so you may get, it will drop in for X, it will drop into a 0.0500 molar. So what will happen to Y? They will have an increase. Okay, they will have an increase in 0.0500 mole per dm cube. Anyone who can, do you understand? All of you. Okay, so you may find that X and Y should be in mole ratio 1:1, but you may find that X drops and Y increase. So X should be on the left hand side, while for the Y should be on the right hand side. So it is a reactant and product respectively. Can you get my point? So this is the first one, and second is on EZ, right? So you can see that EZ, so it will have an increase in what? In how many? In how many units? It will be the increase in about 0.25. It seems it's a half of it. Okay, so this one, what I want to tell you is on this one, increase in 0.0250. So which means that EZ, it is just half, right? But once you are going to find out the overall reactions, you have to multiply that by 2. So C is the answer. You understand? You understand? Okay. So you take a look on question 9. Question 9. This one. What is the average rate of reaction between 0 and 100 seconds? Yes, the answer is B. Yes, the answer is B. So can you draw me the mathematically, right? To draw me some lines, how would you get the answer? Mathematically, what is that? Yes, 100 seconds, you draw a vertical line, and then actually we have got the function. Can you see that? We have got the drawing function, you may use the straight line. Yes, Lei Tong good. So nice, right? So you may find that that triangle. Can you see that? This is a triangle. That while you are going to get this slope, okay, at 100 seconds, and what is the change of the amount? What's the change in amount? It's about 35 cm cube. Can you see that? So it is that too. So the slope it is calculated as 35 cm cube over 100 seconds. Here comes answer B. Got it? Got it. Chen Weihou, I know that you study mathematics well. Give me coordinate. Okay. So how about number 10? Number 10, the last question. Take a look. Last question, number 10. Suppose the rate of consumption of X2, a very authentic question, right? X2 is this consumption 0.090 mole per dm cube per second. How about the rate of formation of ammonia? So the formation of ammonia is here, right? So you may check the ratio. So what will they form? So you have got one portion to have a drop of this formation. Oh, sorry, hydrogen is here. I marked it wrong. It's nitrogen. I've mistakenly treated as a this one. Try to take a look. Again, this one is hydrogen. We've got 3 portions. Okay, 3 portions of hydrogen. We have got a drop of 3 portions. Okay, so we've got 0.090. Here comes ammonia. Ammonia, we've got 2 portions. So that will be increase, right? 2 portions only. So this is C. Can you get my point? 3 portions altogether, 0.09. 2 portions is what? 0.060. Right? Okay, so 1 portion, what is that? 1 portion is 0.030. Can you get my point? Questions? How many of you think that you feel comfortable with those 4 MCs? Yes, that's right. Chen Weihou, you just listen to my saying, right? Well, you memorize it. So how many of you think that you are quite fine with those 4 MCs? Could you please put up a hand? Please put a tick, actually. Please put a tick for easier, right? Tick. Yeah. 朱振輝 趙家明 Yeah. 盧少華 Yeah. Nice. How about 陳俊熙 余子豪 李卓俊 If you find it difficult, you simply put across, let me know. 袁天佑 What do you think? Oh, where is 蔡俊明? Where is 蔡俊明? Who else? Who else is absent? It seems somebody is not here. Sleeping? You better wake him up, okay? Just send a message to him, or maybe use whatever means to make it wake up. Thank you. Who else? We have got 21, so you should have somebody who is missing. Who? Oh, sorry. So I don't wait for the other thing people who come. Just go back to. Oh yes, Mjinghou. Yes, that's right. So he's missing again. So what I'm going to do is to introduce to you. Good morning, Mr. Cho. We have got 2 students absent. One is Mjinghou 5A, the other one is Choi Junming 5B. But I don't know. There should be one more guy. I don't know who. Okay, could you please check it for me? Thank you.李健朗, where are you? Yeah, I just think that you just go to the breakfast, right? You didn't move, right? Your computer didn't move afternoon. What do you mean? Now, Today, we are going to introduce to you some of the methods to monitor the progress of a reaction. Because today morning is an easy start, I will introduce to you some easy method, and tonight I will introduce you some other complicated means. What we are going to do is to understand the way to do the experiments, first of all, and second is the mathematical interpretation, right? So what physical quantities we are going to measure? So actually, we have going to monitor the reaction. We have mainly got two ways. One is physical method. The other one is what we call it as a chemical method. Okay, now so you see that all those four methods is physical method. For chemical method, I would like to introduce to you maybe tonight. So what is mean by physical method? Take a look on that four. First of all, change the volume of a gas product, change the mass of the reaction mixture, change the pressure of the reaction mixture, and finally change the color intensity of the reaction mixture, therefore. So why you say that physical method? 李彤 Hi. What makes a difference between physical method and a chemical method? 胡嘉倫, could you please help? What makes a difference between the physical method and chemical method?
No products are formed.
No, sorry, no what?
即係冇新嘅 product are formed.
Oh, no product they are formed. But indeed, the reaction to be monitored is a chemical change. How would you understand by that? Now, using physical property of a chemical, could you please elaborate more? Now, first of all, the reaction, right? The reaction is a chemical change. While for physical method, it is something something like a CCTV. I would like to mention it like this, right? Okay, we've got a reaction mixture. Okay, can you get my point? And then physical method seems like we have got a CCTV. Okay, and try to have your own way to watch what is the change of the amount of substances inside. So what is mean by that? You have got CCTV, which means that we have no intervention of the chemicals inside. So can you get my point? So we do not change anything. We do not alter. We have not changed the reaction. We do not disturb the reaction and try to observe it at an angle. Can you get my point? So what is mean by observe at an angle? Seeing is just one of them, right? But it is not just seeing because of the nature of a gas. For the convenience of the scientists, you have to take a look on the equation and try to see what will be the change in the physical quantities of certain things. So we will choose different method. We choose different method. So you may see that we have got volume of gaseous product, which means we have got a formation of gas. So you may use this method. And you will have a change in mass of the reaction mixture, which means they will have a drop in the mass of solution mixture. But wait a minute, Mr. Chi, how come the mixture will drop in mass? Isn't it that the mass is conserved? Yes, it's conserved. But how come while you monitor the change in mass of the mixture, we have got a chance to have a drop? What happened to the loss in the mass? What are they? Yes, that's right. Good. Gas. So again, this one will deal with any gas form for this. So these two it seems like a complementary form of one another. How about third one? The change in the pressure of the reaction mixture, you are going with a gas, the gaseous reaction. But you are going to check the total number of moles of reactant that should be not equal to the total number of moles of product. So what is meant by that? For example, if you are going to have this reaction, hydrogen gas, bromine gas to form HBr, we cannot use this for this reaction. You cannot use this method 3 to monitor the rate of reaction, simply because altogether, okay, we have got the mole ratio 2 to 2, right? What I want to mention it is the reactant side, we have got 2 mole, while the product side is still 2 mole. So there will be no change in the total pressure of the system over time. Can you get my point? So this one is not a suitable method. Remember, could you please write down? It's not a suitable method. So which one is a more suitable method? Can you suggest? Any gaseous formation reaction in which you may use this one? Any examples?
Sulfur trioxide 變 sulfur dioxide 同埋 oxygen gas 得唔得㗎？
Yes, it is the and commonly we are going to deal with that reverse reaction. Now it is SO2, SO2O2 to form 2SO3. Okay, the formation of sulfur trioxide from sulfur dioxide and oxygen. Now this one, how about this one? Is it okay? Yes, that's right. Because is it okay? Take a look. There should be, you have got 2 mole. 2 mole of SO2 plus O2 to form 2SO3. It's balanced, right? We've got 3 moles, and this one is 2 moles of gas. So what will happen when you measure the change in pressure? The change in pressure will increase, it will decrease over time. Okay, will decrease over time. Yes, that's right, you may. And finally, the change in color intensity of the reaction mixture. So what reaction should we deal with? Of course, for the reaction which shows color change, we'll use this one. So you are going to choose it very, very carefully, which method you are going to have, right, while you study the rate of reaction. And this is what commonly seen in your exam, okay? I will ask you, I will give you certain type of equation, and you have to suggest for me what experimental method, what physical method is the best to, is more suitable to monitor the progress of the reaction. Do you understand? So this is what I would like to share with you. And today, this time is running short. I'm not quite sure that I can introduce them, or just give you have an overview of those, right? Therefore, and today in those several minutes, I would like to introduce you in detail how will you carry out the experiments. Now, first of all, is take a look on this one, 36.4. Now, this one, for this type of reaction. So you may know that the focus point is calcium carbonate react with dilute hydrochloric acid. The point of our interest is usually CO2, right? Because CO2, the gas will form and expand this the system. So what you're going to do is to put a gas syringe, okay, and you monitor the change of volume of the gaseous product over time. And so you may get the rate of reaction. Especially, what I want to mention is rate of the formation of CO2. Okay, do you understand? So you may use this one, very easy. So the way to do the experiments, it is rather difficult. So you may see we've got a thread with a small tube. Why is it like that? Okay, I will show you the video shortly. Now take a look. Now, Do you understand? Do you understand what is that? So the reaction we are going to consider is the, take a look. Quite difficult. So the reaction we are going to consider is this one. So you are going to have this setup and try to see what happened to this. That do you know why we have got a thread here? Now the setup is very, very similar. Why we have got a thread here? Actually, do you know? We've got a thread here. Why? And we have got the tube. Now, how is this design similar to what we just mentioned? Now, for the video, the reaction is the magnesium ribbon react with HCl, is it? With Expt. Any Expt can do. HCl is okay, H2SO4 is also okay. So we may get magnesium chloride together with hydrogen gas. What are they in common? Is that we have got you are going to measure the change of production of the gas. And the purpose of using this thread is to what? Yes, to measure the gas produced accurately. What is mean by accurately? Now, could you please imagine what will happen? Now, if I don't have any thread, I directly put magnesium ribbon into the Expt. So what will happen to the first few seconds? What I mean is of the data. What happened to the first few data? Now, imagine the graph. What will happen to the graph, right? You're going to have the graph something like this. So what will happen if I have got the two chemicals without any isolation? So what will happen? Before you start the stopwatch, the reaction have proceed. Gas leak, yes, that may be. What else? This is what I've just mentioned, right? In case I have got all so-called everything ready, so what will happen? Now I put that magnesium ribbon or maybe put like calcium carbonate inside that. The reaction has already started, right? Once we have got the direct contact between the two chemicals, the reaction will have started, but everything has not been ready. So what you just measure about the first few data may not be projected, may not be shown as this. Can you get my point? So you are going to carefully design when the reaction can start. So you can control it by yourself. How? Try to have certain type of isolation. Now this is one of them. I use a thread. Now, so you recall your memory about that. You use a thread. You have got a magnesium ribbon, and Expt is here. And you will use the help of a stopper here, and which is connected to the gas syringe. Right, this is one of them. Okay, it's gas syringe. So what will happen to this method? Now, do you think which method is best? What do you think? Which one will have a less errors? If you consider anything like gas leakage or what? Original one. What does it mean by original one? Which one? The one on the blog or the one in the video? Test tube used. This one is better. But if you take a look on the test tube, okay, the size of a test tube and with the thread. Now, I do think that if you use this one, I will have a slight modification. Anyone who can suggest how would you slightly modify this setup? If I were you, I would do that slight modification in order to prevent anything like gas leakage. How? Anyone who know? Now I do the same thing to gas syringe. And we have got two things. One is exit, right? The other one I would like to show you is on here. I would like to show you the material here, right? In a very small plastic barrel. Okay, maybe small, even smaller test tube. So you may get calcium carbonate. So do you know my tricks? Very small, smaller than that, and no thread will be connected. Because once I want to release the thread and I try to get mix of the two, unavoidably the gas will leak out. Okay, the gas will leak, and which will affect the reading. Can you get my point? So by our method, how will you make the reaction start? Some of you don't understand. Anyone who can tell? How? Yes, very good. Shake. So the technique of this is very simple. Shake down. So what you're going to do is to have a test tube with the very small plastic barrel in which it already gives isolation. So I would like to tilt at an angle. Okay, tilt at an angle and shake. It's not sway. Shake. Shake is always mean by up and down, right? No need. You just tilt at the angle and swell. Okay, at a certain angle until this plastic barrel drop. They will fall down. Once they fall down, okay, those chemicals, they will have a direct contact with exit. So it's not the end. You are going to swell it. You are going to swell it frequently until those calcium carbonate underneath the veil can also be dissipated throughout the whole reaction mixture, such that the reaction can proceed. Do you understand? Can you get my point? A way of design. It's a matter of design. How will you make a better design? For those who understand what I've just said about the comparison of the three method, okay, could you please put a thumbs up here? If you don't know, just down. You understand? Just two. Coffee break. I just mentioned something. I just mentioned 2 pages only. Who said you need a coffee break? I check in. How about the other 7 guys? Not here. Oh, that means I've spoken too much. Okay. Oh, so that's fine. I don't want to mention too much simply because Nigeria has such a suggested, right? I said too much, right? It's your turn to say more. Yeah, most of you can get what I mean, right? Good. So this is what I would like to talk to you. So the curve will be something like this. Remember the curve of the y-axis. Take a look on the y-axis. They will show you the different physical quantities. This time we are going to have the volume of CO2 to be measured over time. Okay, so you are going to see what you're going to measure and change it accordingly. Do you understand? So we have got that 3 slope like this, and in your exam, you will really ask you that type of the difference in the 3 slope. How come there is a change in the slope? So what are they? The first of all, the slope of the tangent to time is equal to 0 is steepest, which means the initial rate is the highest, and the reaction rate drops, okay, decreases until it becomes 0. The curve goes flat. The question is why? Why? Can you tell? Why we have got that curve, but not a straight line? Instead, it is a curve. At this moment, why is the reaction very fast? It's the fastest, right? Why? Let's check in. What is mean by surface area large mole reaction? You mean the chemical? Now for the reaction to start, besides talking about the solid, what other chemicals are there? The other one is what? Exit. So what happened to the time is equal to 0? What physical quantities will affect the rate of reaction? At this ballpark. Why? Yes, concentration. Yes, that's right. The concentration of exit is the highest. Okay, so that's why the rate of a reaction is the highest, right? So you may find that. So after that point, what happened? Because I consume some of the exit, so the concentration of exit, they will drop over time. So the rate, they will drop, right? So I don't want to put it here, right? Because it's rather confusing. I would like to write down as highest rate. Okay, highest rate here and drop. And finally here, what will happen? Rate at n equal to 0, which means what? The reaction is complete, right? What is mean by the reaction is complete? In terms of the use of chemicals. Maybe either exit of the solid, which means it's calcium carbonate, has been used up. Okay, so which means that the rate of the reaction becomes 0. So yes, it's reflected by the flattening curve here. Do you understand? Do you understand? Okay. So you take a look on the next page. This is the change in volume of the gas. So of course, you know that it is a complementary method is to monitor the change in mass of a reaction mixture. The same chemical, can you see that? The same chemical, but the change in the design. Okay, you need not consider anything about a gas syringe, right? But instead, we have got cotton wool here. So what is that? To prevent the exit from spraying out, and at the same time, I allow carbon dioxide to escape. So what will happen during the course of reaction? The CO2 will come out, and what will happen to the electron bars reading? They will drop. Okay, because we cannot weigh the mass of CO2 anymore. They will leave the system and go to the air. So what will be left behind is just the salt and water, and together with unreacted carbonate and exit. And over time, what will happen? The total reaction mixture will decrease until it levels off. Do you understand? So that's why you are going to remember that two design, and you are going to record the balance every certain time interval and the reaction finish. So that's why once you know, how you know that is finished, you're going to take more data, right? You're going to take more data such that, and you may find that it levels off. So you know that the reaction has come to an end. Okay, so you still need to take few more data until it flattens, the curve flattens. Do you understand? So this is the graph. Now this graph, it is just the complementary versions of the one in the bottom. Can you see that? This one, it is the complementary versions with this one. Do you know why? Can you see that? The mass of CO2, right? It's not volume now. Mass of the flux at the content. Yes, this is complementary version. So try to take a look on this. Try to pick up 30 seconds, for example, 30 seconds. 30 seconds. Now, for 30 seconds, how many CO2 has been formed? How much? It's about what? It's about 0.080 gram. Okay? At 30 seconds. Here comes the formation of CO2 0.08. Try to take a look on that. From they will have a drop in the mass of the total mixture. Okay, from this to this. So what is the difference between them? What is the difference between the two? What is that? It is 196.270. How about this one? It is 196.190. What is that? What is the difference? Yes, that's right. It is here comes 0.080 gram, which is in line. It is in line with you know that it represents the change in the mass of CO2. Can you see that? Can you see that? So why is it the same? Because you are going to find out that total mass minus the reaction mixture over time, and you are going to plot that graph like this. So this is the mathematical treatment. If you are going to have this, you're going to this curve, you're going to do the slight data treatment, and you can turn back the curve like this. How? You're going to have the original mixture, which means time is equal to 0. I know the mass, and I use it to minus the mass of the solution mixture at that time, and you can project it into the data, just like this one. Suppose I had dropped it's a 30 seconds, and we have got a drop of 0.08 gram of the mass, which means it is carbon dioxide, and I put them across here. And I do the same thing and collect so many data, and I draw the graph like this. So we will say that these two graphs, they are just complementary of one another. Can you get my point? You know what? So similarly, while you have wait for the finish of the reaction is 90 seconds, the curve is now level off. We have got the increase, right? Increase in 0.110 gram, and you may find the same thing here for 90 seconds here. So you have got a drop of the same amount, the same mass of those reaction mixture. Okay, the drop from this to this, there was a drop in the mass. Okay, the drop in the mass, which means what? It is mass of CO2. Can you get my point? Understand? You turn over to practice 36.2, and I would like to end the lecture today by trying out this one. Take a look on this. So consider the reaction below. This one, can you see that? Methyl oleate is a methyl ester, a very long chain of fatty acid, and together with this. So what is the type of reaction? Go back to OChem. What is the type of reaction? Or slept, or have gone to the bed. What is that? You mean addition, right? Addition, yes, that's right. Or we use the term hydrogenation. Right? This carbon-carbon double bond turns to what? Single bond. Okay, hydrogenation. So at room temperature and pressure, you may use that hydrogenation. How? Is to add hydrogen gas to the chemical together with catalyst. What is that catalyst? Do you know? Can you guess? One suitable catalyst, later. Yes, platinum, very good. Okay. You are more responsive than later. So at room temperature and pressure, the methyl oleate is allowed to react with excess hydrogen gas in the setup below. The hydrogen gas flows from the inverted Vashon cylinder to react with the gas through the tube. So what is that? It is hydrogen, right? This hydrogen and I blow and I put it here, and then let the reaction react, okay? Without oleate and platinum and react, and the reaction can be carried out at room temperature. Now, so the magnetic stirrer of a hot plate is only used for what? For to stir the reaction mixture, the magnetic stirrer. Have you ever tried it in chemistry lab? Now you know what is that, right? We've got a very small tablet, right? Just like what you're going to have a medicine, a very small tablet, but it is a bar magnet. You still with a plastic coating, and I put it into it and I open the magnetic stirrer, and they will move. Okay, they will rotate. So A, explain why the right end of the tubing is placed in the uppermost position of an inverted measuring cylinder. The question is related to this. What is meant by that? The tubing here. Why is it placed on very, very top, but not lower, on here? Can you get my point? The tube here. Why is it placed here? To prevent something happen. What is that? What is that? Leak out of the gas. Where would the gas leak out? Sucking back of what? Yes, that's right. To prevent the sucking back of water. So once the tube has been put it like this way, the opening is here, for example, whenever the reaction starts, what will happen to the hydrogen gas? Right, they will consume it, they will react. So what will happen? They will draw the gas here. So the water level will rise, right? Will rise. So what happens if a water level rise? They will have an occasion where the water will black fall into the tube and go into here. Can you get my point? So in order to prevent something from happening, okay, you're going to put the tube far on the topmost position and wait until the water level rises. Okay? Do you understand? B, the curve below shows the variation of the volume of hydrogen gas. The curve below shows the variation of volume of hydrogen gas is measuring cylinder with time. Can you manage to answer the following? It's just what will happen to the water level inside the, hey, I just mentioned with you, while the reaction measuring cylinder during the reaction. The level rises during time, right? Because it is a reflection of a hydrogen gas to be consumed. Okay, it's consumed. So that's why, because there's a change in the pressure, the water level will increases. Yes, that's right. Everything good. Now, so what will happen to the curve? Which point A, B, or C represent the Rose rapid reaction? Explain your answer. You know it. It's easy, right? It's point A. Why? The slope of the consumption of hydrogen is the highest at that point. So you are going to tell the slope. What does that mean? Slope of what? Slope of this curve, right? So this is one way to answer. Or if you want to mention this part, you are going to tell me the tangent again to the curve at point A is the highest, which means what has been suggested, right? The rate of consumption of hydrogen is the highest. At where? At where? At point A, what does it mean by that? Point A, it is time is equal to 0. And as the highest at time is equal to 0. Okay, so it is what we call that? It is initial rate. Initial rate. initial rate, which means instantaneous rate at time is equal to 0. Okay, so this is what I would like to talk to you here. Questions? Understand? So this is what this is about the first part. Okay, this is about the first part. We have got two reaction. We have got the monitoring method. We've got the two. What are the two? Could you please tell me? What are the two? So we have got indeed we have got so many different way to monitor of the reaction. So we have got that two, change in mass of the solution mixture, okay, or the change in the volume of the gaseous mixture over time, okay. So for further details, I would try to give you these two video, right? And you better spend some time. I give you the link of the two, and try to watch it by yourself. Okay, we've got that too, right? We just mentioned that we have got quite a lot more to go. So many different methods. Can you see that? Okay, we have got the first two. I will show you the link into our YouTube. The video we have got the comments part here. I will show that two video the link and try to read it very, very carefully. Try to imagine what will happen when you are having the reactions in the real situation. Okay, is that clear? Maybe I show you the link here, right? For you here first. This is the first link. I will show you the second link. Yes, this is the one. All right. All gone. What do you think about today's lecture? What do you think? 7. How about the others? I just wait until all of you have written down your feeling. 温子維 5， 李健龍 7， 6 陳俊熙，胡嘉倫 8 ，yeah good， 趙家明 7。 Who else? 朱俊輝 have you talked anything? Yes 6。 李健朗 where are you? 係出現。杜少華、黃家豪、李彤、郭內偉、徐家榮、陳偉華 no I remember the 7 right。 余日斌、袁天佑 and also 李彤 you did not tell. Yes, 黃家豪 you would like to sit for the lesson. That's fine. I'll drop E1. So originally, what is that? What was that subject? It's physics, right? Econ. Okay. Oh, so you cannot escape, right? Just focus on chemistry and the remaining elective, right? And strive for the best for next year, 2021 DSE. Oh, oh, how? I know that there should be Yu Yabin, Yuan Tianyao, and Lei Tong has left. They three are too sad, right? To stay here. So I was just to stop it here. Okay, see you guys tonight. Bye bye.